Welcome back. Let's learn about the dot product. All right, so far in Calculus 3, you've seen how we can add vectors, subtract vectors, and how we can multiply a vector by a scalar. But the question still stands, can we multiply vectors together, right? Can we multiply a vector by another vector and get some kind of result? Well, the short answer is yes, but there's actually two different ways to go about multiplying vectors. We're going to look at the first way in this video, which is the dot product, and we'll look at the second method in a future lesson. Okay, and so let's start by looking at the dot product in 2 dimensions, meaning that we have vectors within a 2-dimensional coordinate system. In this case, you can see we have vector v and vector u. Both of them are position vectors of 2-dimensional points. And so if we want to multiply vector v by vector u using the dot product, what does that look like? Well, from a definition standpoint, what the dot product will do is it's going to add the product of corresponding components between our vectors. And so here's what that looks like. We represent the dot product like this. We'll write vector v dot vector u. All right, so this right here represents the dot product of vector v and vector u. We represent this operation with this dot between our vectors. And so the dot product of vector v and vector u will be equal to the x component of vector v multiplied by the x component of vector u plus the y component of vector v times the y component of vector u. And so that looks like this. We'll have v1 times u1, and we'll be adding that to v2 times u2. All right, that's going to be the dot product for vectors in 2D. We multiply the x components of our vectors together and add that to the y components of the vectors multiplied together. All right, it's really not too complicated of an operation. But one thing that you want to take a note of here is that the result of the dot product, v1 times u1 plus v2 times u2, this is going to be a scalar result, right? This is not going to be a vector. Previously, when we did vector addition or vector subtraction, or even scalar multiplication, our result was always another vector. But in this case, when we multiply two vectors together via the dot product, we're going to end up with a scalar value. Now, how that scalar value is useful to us is something that we will look at in later lessons. For now, what I'll tell you is that the result is going to give us an idea about how these two vectors are related in terms of their direction. All right, but once again, we're going to look at the uses of the dot product in future videos. Okay, but now let's take a look at an example of finding a dot product for two vectors. For this example, we have vector v and vector u, where vector v is the position vector of the point 3, 5, and vector u is the position vector of the point -1, -2. So if we want to find a dot product, we'll write it like this. We'll have vector v multiplied by vector u. That dot represents the multiplication of these two vectors via the dot product, and that will be equal to the x components multiplied together. So we'll have 3 times -1, and then we're going to add that to the y components multiplied together. So we'll have 5 times -2. Right, the x components are 3 and -1, so 3 times -1 is right here, and then the y components are 5 and -2, so we have 5 times -2. All right, now we just want to simplify to find our dot product. 3 times -1 is -3, so this is equal to -3 plus 5 times -2, which is -10, so we'll have -10, and -3 plus -10 is -13. So -13 is the dot product of vector v and vector u. And you can see, just like we discussed, the result of the dot product is a scalar value. It's just -13, right? It's not -13 times vector v or times vector u. There is no vector in this answer. It's just a scalar value. Okay, so that's the dot product for vectors in 2D, but what does the dot product look like for vectors in 3D? Well, if we're working with vectors in 3D, and here you can see that we have two vectors that are in 3 dimensions, right? Vector v has 3 components, v1, v2, and v3, an x component, y component, and z component, and vector u also has 3 components, which are the x, y, and z components. So if we have two vectors in 3D, and we want to find the dot product of those two vectors, we want to multiply them together, it's going to be practically the same as it was in 2D, except now we have an extra pair of components to account for. the dot product is still going to be the addition of the product of the corresponding components. So we're still going to have v1 times u1, v2 times u2, and add those together. But now we're also going to add on a third term of v3 times u3, the product of the z components. All right, so here's what that looks like. The dot product of vector v and vector u in 3D will be equal to v1 times u1 plus v2 times u2 plus v3 times u3. All right, and so that is the dot product in 3 dimensions. It's really not all that more difficult than the dot product in 2 dimensions. We just have that extra term that accounts for the z components of our vectors. All right, so nothing else really changes. We still multiply the x components and add it to the multiplication of the y components. We just add on v3 times u3, and the result of the dot product is still a scalar value. The dot product will never give you a vector, whether that's in 2D or in 3D, you will always get a scalar. Okay, so let's take a look at an example. This time we have that vector v is equal to 3i minus 2j plus k, and vector u is equal to negative I plus 4j minus 5k. All right, now these vectors are given to us in standard unit vector notation, but the rules of the dot product still apply. We'll multiply the x components together, add that to multiplying the y components together, and add that to multiplying the z components together. All right, it's the same exact thing, except the components that we're looking for here are the coefficients of I, j, and k. All right, so if we want to find the dot product of vector v and vector u, where those two vectors are 3D vectors, we'll multiply the x components together. So we'll have 3 times negative 1, and then we'll add that to multiplying the y components together. So we have negative 2 and 4. So we'll have negative 2 times 4, and then we'll add that to multiplying the z components together. So we'll have 1 times negative 5. All right, so we'll have 1 times negative 5. All right, now just to make sure that that made sense, the x components of vector v and vector u are 3 and negative 1 because we have negative I, right? So the coefficient of I here is just negative 1. So our x components are the coefficients of vector I, so we have 3 times negative 1. Then for the y components, those will be the coefficients of j, so we have negative 2 times 4. And then for the z components, those are the coefficients of k, and so we have 1, since this is just plus k, the coefficient is 1. And this coefficient is negative 5, so we have 1 times negative 5. Okay, so now if we simplify, 3 times negative 1 is negative 3, so this is equal to negative 3 plus negative 2 times 4, which will be negative 8, and then we'll add that to 1 times negative 5, which is negative 5, so we'll have plus negative 5. And negative 3 plus negative 8 is negative 11, plus negative 5 is negative 16. So the dot product is equal to negative 16. All right, and so as you can see, that is a scalar value. Negative 16 is not a vector, it's just negative 16. It's a scalar. That is the result of multiplying vector v by vector u via the dot product. Okay, and so that's really all there is to the dot product. It's just as simple as adding the product of the corresponding components of your two vectors, and the result of that will be a scalar. Okay? Now, before we look at some more complicated examples involving the dot product, there are actually some properties of the dot product that you should be aware of first. And so let's take a look at those next. All right, so there's 5 different properties of the dot product that you should be aware of. And so for vectors v, u, w, and scalar c, here is what we know about the dot product. For the first property, if we're multiplying vector v by vector w via the dot product, right, that's what this dot represents, the operation of the dot product, that would be the same as the dot product of vector w and vector v. All right, so it doesn't matter the order of your vectors when you perform the dot product. Whether you have vector v times vector w or vector w times vector v, it's going to be the same thing. They are going to be equal. And sometimes this is called the commutative property of the dot product. All right, the order in which you perform it does not matter. V times w or w times v, it's the same either way. All right, now for the second property, this is going to be our distributive property. If we have a vector u multiplied by the addition of vector v and vector w, that would be the same as multiplying vector u via the dot product to each of those vectors individually and adding them together. So that looks like this. We'll have vector u multiplied by vector v, and then we'll add that to vector u multiplied by vector w. All right, so the dot product is distributive. Vector u times the addition of two other vectors is the same as just multiplying that vector by both of those vectors individually and adding them together. All right, u times v right here plus u times w right here. Okay, so now let's look at the third property. The third property deals with scalar multiplication. If we have that scalar c multiplied by the dot product of vector v and vector w, that would be equal to these two other statements. We could have that scalar c multiplied by vector v and then multiply that by vector w, or we could also write it like this. We could have vector v multiplied by that scalar c multiplied by vector w. All right, in other words, it doesn't matter the order in which you multiply this scalar by these vectors that are being multiplied together via the dot product. You can multiply it after you perform the dot product, or you can multiply that scalar times v right away and then perform the dot product, or you can multiply that scalar by w first and then perform the dot product between v and whatever that vector is. All right, so it doesn't matter the order in which you multiply a scalar by two vectors that are being multiplied together via the dot product. Okay, now for the fourth property, we have the zero vector multiplied by vector v via the dot product. That is going to give us a scalar of 0. All right, because the zero vector, if you don't remember, the zero vector looks like this. It's the vector where both components are 0. So you'd have 0, 0, or in the case of 3D vectors, all three components are 0. So I could erase this and add on another 0, but either way, if you were going to be calculating the dot product between the 0 vector and another vector, you're going to be multiplying 0 by the corresponding components of vector v, and that's just going to give you 0 every time. It doesn't matter what the components of vector v are, you're going to have 0 times v1 plus 0 times v2 plus 0 times v3, which is just going to give you zeros all across the board. And so the result will just be 0. Okay, so performing the dot product with any vector and the 0 vector will give you 0. Okay, and then finally, we have our fifth property for the dot product. And the fifth property is that if you multiply a vector by itself via the dot product, right, if we have vector v times vector v, that's going to be equal to the magnitude of vector v squared. And the reason why this is true may not initially be clear, but let me show you why it's true. If we assume that vector v is a position vector of the point v1, v2, v3, then the dot product of that vector with itself would look like this. It would be equal to v1 times v1 plus v2 times v2 plus v3 times v3, right? We multiply the x components together, so we'd have v1 times v1. Then we add that to multiplying the y components together, which in this case are both going to be v2, since we're multiplying the same vector by itself. And then we add that to the multiplication of the z components, which in this case are both going to be v3. So if we simplify, this would be equal to v1 squared plus v2 squared plus v3 squared. And so how do we get from this to the magnitude of vector v squared? Well, if you remember what the magnitude of vector v is equal to, it's equal to the square root of the sum of the components squared. So we'd have v1 squared plus v2 squared plus v3 squared, right? This is how you calculate the magnitude of a vector. Notice that the sum of the components squared, that's underneath this square root, are found right here from the multiplication of vector v by itself via the dot product. So a way that we could rewrite these terms right here would be like this. We could have the square root of the sum of those components squared, v1 squared plus v2 squared plus v3 squared, and then take that whole quantity and square it, and this would still be equal to this right here, right? When you square a square root, they cancel each other out, and you're just left with the terms inside the square root, which is v1 squared plus v2 squared plus v3 squared, which is what we have right here. So if we can rewrite this to be like this, and that represents the dot product of vector v with itself, notice that the square root of v1 squared plus v2 squared plus v3 squared is the magnitude of vector v. So that's why we can replace this with the magnitude of vector v and square it to get this right here. That is where this property comes from. All right, if you multiply a vector by itself via the dot product, that will be equal to the magnitude of that vector squared. And this is a very important property to know. These other ones are a little bit more intuitive. You don't really have to memorize them per se. You just kind of get used to working with these properties. But this fifth one is a little bit more important. You really want to make sure that you know this because this becomes very handy later on in Calculus 3. All right, knowing that the magnitude of a vector squared is equal to the dot product of that vector can be useful in certain scenarios. And another result of this property, let me show you this real quick. Since we know that the dot product of a vector in itself is equal to that vector's magnitude squared, we could solve for that magnitude by taking the square root of both sides of this equation, and we would find that the magnitude of vector v is equal to the square root of the dot product of vector v with itself. All right, so you could find the magnitude of a vector this way as well. You could take the square root of the dot product of that vector with itself. All right, so that's something that you might want to keep in mind as well. But with that, those are the 5 properties of the dot product that you need to know, that you need to be aware of. And so before we close out this lesson, let's take a look at one more example where we practice using the dot product. Hey there, real quick, before we get to the next part of this lesson, if you find my tutorial videos here at JK Math to be helpful and you want access to more content such as exclusive bonus videos and dark mode versions of my videos, I'd invite you to check out my membership site JK Math Plus, where all of that content is available. To learn how to join and see a full list of everything you'd get access to as a member, you can head over to jkmathematics.com/plus. I'll have a link for that in the description of this video. Okay, so if you're interested in becoming a member, feel free to check that out. It's a great way to support me and the tutorials I make, as well as a great way for you to learn math better. But for now, let's get back to the lesson. All right, so here's our example problem. We have for vector A, which is the position vector of the point 2, 1, negative 3, vector B, which is the position vector of the point negative 4, 7, 3, and vector C, which is equal to 4i minus 7j plus k, we want to find the following. And I actually have a third thing that we want to find as well, but I'm going to wait to show you that one until we complete these two right here. Okay, so we have 3 different vectors. 2 of them are given to us in the standard notation, and then we have this third one given to us in the standard unit vector notation. All right, now to make things easier for ourselves, I'm actually going to rewrite vector C to be in the same form as vector A and B. So I'm just going to rewrite vector C as this. We'll have 4, negative 7, and 1 as the components of that vector, right? We just took the coefficients of I, j, and k to get our corresponding x, y, and z components. And so now that we have all 3 vectors in the same form, let's work on evaluating some of these expressions that we have here. First off, we have vector A multiplied by the addition of vector B plus vector C. Now, if you know the properties of the dot product, then you know that another way that you could calculate this would be to distribute vector A through both of these vectors, right? You can multiply vector A by vector B using the dot product and then add that to the multiplication of vector A and vector C using the dot product. Okay, so that looks like this. You could have vector A multiplied by vector B, and then you could add that to vector A multiplied by vector C. All right, and that's how I'm going to go about this problem. You could certainly add vectors B and C first, and then perform the dot product between that resultant vector and vector A. But since we just went over the properties of the dot product, I think it would be a good idea for us to practice using them and calculate this way. All right, so let's perform the dot product between vectors A and B first. This will be equal to multiplying the x components together. So we'll have 2 times negative 4. So I'll write 2 times negative 4. And then we'll add that to the y components multiplied together. So we'll have 1 times 7. So I'll write 1 times 7. And then we'll add that to the z components multiplied together, which are negative 3 and 3. So we'll have negative 3 times 3. All right. And then we're going to add that to the dot product of vector A and vector C. So now let's do that. We're going to multiply the x components of vector A and vector C together. So we'll have 2 times 4. All right, so we'll have 2 times 4. Then we'll add that to multiplying the y components together. So that will be 1 and negative 7. So I'll write 1 times negative 7. And then we'll add that to multiplying the z components together, which are negative 3 and positive 1. So we'll have negative 3 times 1. All right, so now all there's left to do is simplify. 2 times negative 4 is negative 8. So this is negative 8 plus 1 times 7, which is 7. So we'll have 7 plus negative 3 times 3, that's negative 9. Then we have plus 2 times 4, which is 8. So we have plus 8. And then we have plus 1 times negative 7. So it will be plus negative 7. And then we'll add negative 3 times 1, which will be negative 3. All right, now to simplify further, notice that we have a negative 8 and a positive 8 and a positive 7 and a negative 7. Those will cancel out, so I'm just going to cross those out. And we're just left with negative 9 plus negative 3, which gives us a final answer of negative 12. And so negative 12 is the dot product of vector A multiplied by the addition of vector B plus vector C. Okay, now if you want to check to make sure that this property of the dot product that we used is true, you could go ahead and add vector B and vector C together, and then do the dot product with vector A, and you should get the same answer of negative 12. And so I would encourage you to try that to see that this property is true. But now that we found what this is equal to, let's move on to our second part here. Here we have the dot product of vector A and vector B multiplied by 3 times vector C. All right, now in this case, I'm going to choose to do the dot product of A and B right away, and then we'll multiply it by 3 times C. And we already calculated the dot product of A and B earlier, right? It's these 3 terms right here. These 3 terms came from multiplying vector A by vector B via the dot product. So we can just rewrite those terms again. They resulted in negative 8, 7, and negative 9. So this will be equal to negative 8 plus 7 minus 9 times 3 times vector C. All right, now negative 8 plus 7 is negative 1, and negative 1 minus 9 is negative 10. And so we have negative 10 times 3 times C. Negative 10 times 3 is negative 30, so this will be equal to negative 30 times vector C. And so now, to get our final answer, we just have to perform this scalar multiplication. We just need to multiply negative 30 by each of the components of vector C. So this will be equal to negative 30 times 4, that will be negative 120. Then we have negative 30 times negative 7, that will be positive 210. And then we have negative 30 times positive 1, so we'll have negative 30. And that right there is the result of multiplying the dot product of vector A and vector B by 3 times vector C. Okay, notice that in this case our answer was a vector, and that's because the dot product of A and B resulted in a scalar value, and we're multiplying that by another scalar value, which is being multiplied by a vector. All right, and scalar multiplication will always give you a vector. Okay, let's take a look at one more thing for us to calculate using the dot product. Lastly, we want to find the result of squaring the magnitude of vector A plus vector B and adding that to the magnitude of vector A minus vector B squared. All right, now this is where one of those properties of the dot product comes in handy, right? Remember that we said that the magnitude of vector V squared is equal to the dot product of that vector with itself, right? So if we're squaring the magnitude of these two vectors, and vector addition and subtraction will give you a vector, then all we have to do is find the dot product of those resultant vectors and add them together. All right, so this would be equal to vector A plus vector B multiplied by itself. So we'll have vector A plus vector B, right? The magnitude of that vector squared is the same as finding the dot product of that vector with itself, and the same thing is going to occur for this magnitude squared, except now we have vector A minus vector B, so this will be added to vector A minus vector B multiplied via the dot product by itself, so we'll have vector A minus vector B. Okay, so now if we want to find the result of these operations, what we need to do is first find vector A plus vector B and vector A minus vector B. All right, so vector A plus vector B, let's do this on the side here. That's going to be equal to the sum of the corresponding components. So we'll have 2 plus negative 4, that's going to be negative 2. So we'll have negative 2 comma the addition of the y components. So we'll have 1 plus 7, which is 8. And then we'll have the addition of the z components, which are negative 3 and 3, which becomes 0. All right, so that's vector A plus vector B. Now let's find vector A minus vector B. That's going to be equal to the vector where we subtract the corresponding components. So we'll subtract the components of vector B from vector A. So we'll have 2 minus negative 4, and that will be the same as 2 plus 4. right? If you're subtracting a negative number, it's the same as adding the absolute value of that number. So 2 minus negative 4 is 2 plus 4, which is 6. And then we'll subtract the y component. So we have 1 minus 7, which is negative 6. And then we'll subtract the z components. So we'll have negative 3 minus 3, which is also negative 6. Okay, so now using these two vectors, we can perform these two dot products. This vector right here is the same as this vector, and this vector right here is the same as this vector. All right, or both of those vectors for both of those dot products are both equal to those vectors. All right, so if we're going to perform the dot product on this vector right here, we're just going to be adding together the components squared, right? Because we'd be multiplying the x component by itself, adding that to the y component multiplied by itself, and then adding that to the z component multiplied by itself. So this will be equal to negative 2 squared plus 8 squared plus 0 squared. That's the result of that first dot product, and then we will add that to our second dot product, which we'll find by multiplying this vector by itself. So we're just going to be adding together these components squared. All right, so we'll have 6 squared plus negative 6 squared plus negative 6 squared. And so that is the result of that second dot product. Okay, now if we simplify, this will be equal to positive 4 plus 64 plus 0 plus 36 plus 36 plus 36, right? Negative 2 squared is 4, 8 squared is 64, 0 squared is 0, 6 squared is 36, and negative 6 squared is 36, and we have that twice, so we have 2 more 36s. All right, now 4 plus 64 is 68, and then if we add 36 3 times, that will give us 176. And so finally, we now know that this is equal to 176. That is the result of squaring the magnitude of a plus b and adding it to the magnitude of a minus b squared. Okay, and so with that, that is it for this lesson on the dot product. But if you want to see some more examples of using the dot product, feel free to check out my examples video that I'll have linked here on the screen. If you have any questions, feel free to leave those in the comments. But if you don't have any questions, this is all I had for now. So I will see you next time.